So, good afternoon, everybody. My name is Peter, and I work for Cake Solutions. We are a consultancy company focusing on building reactive and data processing applications using technologies such as Scala, Akka, Spark, and many others. I have a pleasure to work with a number of companies, and quite often I have been asked to tackle problems they faced. And some of these problems were quite repetitive. So I picked a couple of them and made a talk about it. I'm going to talk about topics like actors versus futures, serialization, supervision, graceful shutdown, distributed transactions, long-tail latencies, and that's it. After that, I've got a short sections with quick tips, which are basically topics I'd like to talk about, but I do not have enough time for that. Lastly, I will go from the most basic topics to the more advanced, so I hope everyone will find something interesting. And also, in the end, there's definitely a space to share problems you guys faced. So let's move on. Constraints liberate. Liberty is constraint is the name of an excellent talk by Gunnar Bjarnason he gave like a year ago at Scala World Conference. Apart from many things, he talks about how constraints liberate us and how we should use the least powerful and the most precise abstraction, which does the job for us. And this makes perfect sense in the context of actors versus futures. So this is what our toolbox looks like. On one side, we have a future, and on the other side, we have actors. Futures is a strongly typed local abstraction for concurrency. It returns just one value by definition. On the contrary, actors are very dynamic. They are not usefully typed, and the receive method is a partial function from any to unit. So basically, give me whatever, and I maybe do some side effect. Therefore, actors are not functional nor composable. On the other hand, they are location transparent, and they have nice resiliency mechanisms like watching, recovery, supervision, and so on. Additionally, we now have Akka-type, which tries to tackle shortcomings of the vanilla actors. But right now, it's still very experimental and definitely not an option for production systems. But it is an interesting library. You may take a look. And by the way, don't confuse this with typed actors, which are deprecated a while ago. Nice middle ground are Akka streams, which are a static way how to define processing. They are well typed, and they also offer back pressure. So as you can see, Akka gives us a couple of options. Some of them are less powerful, constrained, and easy to use. And some of them are very powerful and with fewer constraints. But as I said in the beginning, we should always try to use the least powerful abstraction, which does the job. Here we can see some common actor use cases. First one is the state management, which is obviously a very good reason to use actors. Other good reasons why you'd like to use them are another core Akka features like location, transparency, resilience, and so on. And actors are also by their nature great if you want to take advantage of single writer principle, and they can be used as in-memory log-free cache as well. Another very common usage of actors is obviously sharding. And futures should be used in cases when we need just local concurrency. Surely this is achievable by actors easily, but futures are much easier to use. Futures requires file-less writing, and we can take advantage of functional approach. So we can enjoy type safety or feature composition, and all these things we love. So do not overuse the actors. As you probably know, Java serialization is slow, footprint heavy, and has Scala version binary compatibility issues. And as you may know as well, Java serialization is the default in Akka. And that's pretty bad. There are two main reasons why we want to serialize data when using Akka. First one is sending data through the network. Obviously, Akka doesn't serialize messages which are sent locally. Why would it? So we have an actor which serializes message and sends it to another actor. The second actor deserializes message, creates a response, serializes it, and sends it back. This round trip is called ping pong test and is often used for the evaluation of serialization libraries. The second use case is persisting data into local storage. I had a client last year, or maybe a year before, and they had performance issues regarding Akka persistence. They told me it took more than a minute to create their persistent actors. A minute, seriously. But yeah, it is certainly possible. Just imagine the actor has a quite complex state, and it uses Java serialization. Then you'd add not using snapshots at all, and here we are. So let's have a quick look at this graph. It compares round trip of various serialization libraries. I'm pretty sure it is very hard to read, but so I added the arrow which shows us where the Java implementation stands. And this graph shows us the footprint size. As you can see, the last spot. And by the way, if you would like to see the sources of this, they are in the references slide in the end. And this is how serialized data looks like for a very simple class. The footprint of Java serialization is far bigger even than the footprint of not very efficient format like XML or JSON. And the good question is why it is like that. And the reason is it does not serialize just data, but it also serializes the entire class definition and all definition of all reference classes. It was designed to be simple to use, to serialize almost everything. And also it was supposed to work with different JVMs. But apparently, performance was not the main requirement. But honestly, after 8 major Java versions, it could be a little bit better. When choosing among various libraries, there are a couple of points we should have in mind. The main reasons why we want to avoid Java serialization are its performance and its footprint. But we should also have in mind like schema evolution support, which is really important for real-world systems. And by the way, this is another thing which is very complicated using Java serialization. We should also consider the expected implementation effort, but of course, this varies a lot for different libraries. But in general, it is pretty hard to beat Java serialization. The decisive point might be the requirement for human readability. It decides if we can use JSON or XML, or if we can go for one of the binary formats with all their advantages. The last point I included here are the language bindings. This very depends on your particular use case, but obviously, as we are in Scala Days, all libraries I want to mention have Scala APIs. JSON is the most used human-readable format these days. Surely, there are some others like XML or CSV or whatever, which certainly have their use cases, but I will go mainstream. Surely, it has disadvantages. It's relatively slow and bulky, but if you need to have a human-readable format, it is a good way to go. And the good thing is that there are so many great libraries available. For binary formats, we have 2 options. Firstly, schema-less formats, meaning data are sent together with corresponding metadata. The main advantage is we don't have to define schema, so it is almost like using Java serialization. But performance-wise, these formats are a very different story. As an example, we can have Cryo and its Scala library named Chill. And by the way, setting up this in Akka is a matter of minutes. We can also consider binary JSON formats like message pack or BSON, which basically trade readability for performance. Binary formats have their schema defined by some kind of DSL, so they offer great performance and minimal footprint. And they usually provide built-in support for schema evolution. A popular choice is Protobuf and a couple of related projects like Flat Buffers or Captain Proto. Another representative might be Apache Thrift, which was originally developed by Facebook, or Apache Avro, which is primarily used in Hadoop ecosystem. So let's wrap this up. I like to say you should always, or if you plan to go to production at least, replace Java serialization with something else. This very depends on your particular use case, so I leave it up to you. But if you want to have like a fake by recommendation, go for one of these, JSON 4S, Cryo, or Protobuf. All of them are great and proven libraries, and they should work for you. This topic is not about what people do. It is more about what they don't do, but I think they should. I like to make a brief motivation about supervision. Honestly, I have a feeling that supervision is one of the ACA's fundamental ideas which is not used as it should. So let's have a very quick recap. These are two top-level actors. We create them by calling actor_system.actorOf. We call them top-level because they are created by the system, not by another actor. One of the key points of actor supervision is that every actor, or almost every actor, as you will see in a minute, has a supervisor. So who supervises these? As you guys probably know, these actors are implicitly supervised by the guardian, or sometimes referenced as the root actor. And the second key point of supervision is that every actor can also be a supervisor, and every actor supervises his children. So when we start creating actors, not by using actor system, but by using actor context, we can get something like this. So for example, C1 and C2 are supervised by B1, and B1 is supervised by A2, and so on. So that was the hierarchy. And now let's talk about what is it good for. The point is that every time an actor throws an unhandled exception, his supervisor may decide what to do with that. He can tell the actor to ignore it. He can also stop the actor, restart it, or escalate this up to his own supervisor. And he can also apply this not just to the problematic actor, but to all its siblings. And that's pretty much it. So that were the user actors, but we also have system actors. Their job is basically to take care of actor system features, like actor logging, for example. Or they are also responsible for actor system shutdown and all these infrastructure things. But this is not that important for us. I think it's just good to know that it's something like that. And also, if you're wondering what is the /actor on the top, this guy is called root guardian, and it's the only actor which is not supervised. So that was the quick recap what the supervision is, but why do we want that? Basically, there are two battles we want to win. Firstly, we want to separate our business logic and our error handling for having less complex code. And secondly, we want our application to be able to get back to life after something bad happened. Supervision gives us a failure isolation and a system recovery, and therefore, no more midnight calls for us, hopefully. Obviously, I don't want you to push you into using supervision wherever possible. That's probably not a good idea. You guys should always decide what makes more sense in your particular use case. I think a nice guideline how to decide is to split your exceptions into errors and failures. Errors are common events like incorrect requests, problems during validation, and so on. And they are communicated with the client/caller. On the other hand, the failure is an unexpected event within a service that prevents it from continuing to function normally. Failure will generally prevent responses to the current and possibly all following requests. Failure should be reported to the supervisor. The client cannot do anything about it anyway. As an example, we can have database failures, network partitions, hardware malfunctions, and so on. And by the way, this is not something I just made up yesterday. This is taken from the Reactive Manifesto, so the core idea is really old. Regarding supervision, we may have a problem. What to do with an active state during restarts? There is this pattern for it. Basically, it is just a simple guideline you should try to follow, stating that if an actor carries important internal state, then it should delegate dangerous tasks to its children to prevent the state-carrying actor from crashing. Sometimes it might make sense to create a new child actor for each such task, but that's usually not needed. Another thing regarding supervision, which is often forgotten, is the Backoff Supervisor. Usually, when we want to restart an actor, we want to do it as soon as possible. And not surprisingly, this is the default ACAS behavior. But there are certain use cases when we want to wait a little bit. Let's say some external resource is not available, and we need to give it some time to start up again. Typical example is when a persistent actor fails because of a storage failure. Imminent restart would lead to another failure and another restart and so on. So we would effectively DDoSing our system. Backoff Supervisor allows us to restart our actors each time with a growing time delay between the restarts. And it tries to avoid that. As you guys probably noticed, I put a simple example in the slide. It definitely has other config options, but let's keep it simple. So let me go through that. The API gives us two ways how to identify a failure. The first option is what you see in the slide, by an actor crash. But it can also react to an actor stop if it works better for your needs. Then we have to define the actor you want to supervise. I think these parameters are quite clear to all of us, but maybe one thing worth mentioning. As you can see, we are creating the supervised actor by the supervisor. So it might look like that the supervisor gets messages intended for the actor. But obviously, it is not like that. It is designed to be as transparent as possible. So the user messages are forwarded to the child actor. And this is how does the actual Backoff config looks like. We can define the initial duration, which is set to 3 seconds here. And also, we have to bound it somehow. So in this snippet, the cap is 30 seconds. As I mentioned, the fail actor would be restarted in increasing interval. In this case, it will be after 3, 6, 12, 24, and finally after 30 seconds. And this is the last bit I want to show you here. It's random factor parameter. Imagine that we have a couple of hundreds of actors relying on external resource, and it goes down, but after some time it recovers. So what happens now? After the next tick, these hundreds of actors simultaneously hit the resource, and this may break it again. So we have an option to add additional random delay or noise, if you will, to it. This may help in some cases. This O.2 value means that it adds up to 20% delay. So, yeah. And that's pretty much all I wanted to say about the Backoff Supervisor. So let's summarize it. ACA provides supervision, which allows us to create rich hierarchies to separate business logic and failure handling. And also try to have in mind that something like the Backoff Supervisor exists. Another topic I like to discuss is Graceful Shutdown. So let's say we have thousands of sharded actors on tens of nodes, and we want to shut one of them down because of maintenance or hardware issues or whatever. Essentially, we want to do something like this, but we don't want to lose data which are already in the node. This operation must be totally transparent to our users. So let's talk about how the procedure should look like from a high-level point of view. I really wanted to show you code samples here, but was unable to squeeze it. But if anyone is interested, they are in the backup slide section in the end. Firstly, JVM gets the shutdown signal, which triggers this whole exercise. When this happens, we tell coordinator the procedure has started. The coordinator is a stateful entity which manages various states of Graceful Shutdown. As I like Akka, in my case, coordinator is implemented as an FSM actor. But of course, you can do it differently. Now the coordinator has to tell local shard regions they have to leave the cluster and wait until it's done. So it has to send Akka's Graceful Shutdown message and watch their lifecycle updates. When it is done, coordinator asks the node to leave the cluster and give singletons a grace period to migrate. Unfortunately, there is no callback for this. So it has to wait specified amount of time. Finally, we can kill the coordinator, shut down the actor system, and let JVM to be terminated. At some point, you will have to add messages for interaction with sharded actors. Just a quick note, if you want to stop the actor gracefully, use passivate. If you need to stop it immediately, use context.stop. And the last thing I want to mention here is the priority mailbox. It is good to have it because it allows your graceful shutdown/command messages to be handled in priority. Basically, it maintains two queues, one for normal and one for priority messages. It also may respond the node is shutting down, so the message can be resent to another node if needed. So that was the idea how it could be implemented. If anyone is interested, some code samples are in the end. But now let's briefly talk about Coordinated Shutdown Extension, which was added to Akka in version 2.5. And this was released like a week ago. I don't think you'll be surprised, but I have to admit I don't have any real experience with it. But I think it might be useful in our case. So basically, what it does, basically it defines a bunch of phases like service stop, cluster exiting, or actor system terminate, and we can register tasks to each phase. And these tasks will be executed at various points during the shutdown. The task is pretty much a function returning a feature of done, which is used just for signaling completion. So we can add pretty much anything into it. For our case, it's important that it also have phases like sharding, shutdown, leave cluster, or actor system terminate, which we can use for the graceful shutdown in a similar way I described like a minute ago. So if this really works, as I hope it does, thank you, Lightbend. This was really needed. So let's have a quick summary. We usually don't want to lose data. Sometimes it's fine, but most of the time we do care about it. We discussed two approaches how to implement this. The first one is the manual one. Its implementation, it is not that hard, but some knowledge is necessary. We need to implement a node shutdown coordinator to handle various states of the shutdown procedure. And also we need to do some integration with our sharded actors. Or we can try to use the super new Akka extension named Coordinated Shutdown. So that's it for Graceful Shutdown, and now the distributed transactions. So distributed transactions, or any situation where a single event results in the changes of two or more separate data sources which cannot be committed atomically. Of course, this definition is very informal, but I think it suits our purpose real well. The problem is, especially for naive implementation, it works most of the time. But there is something named fallacies of distributed programming, in case if anyone of you has not heard about it yet. Please take a look at it. It is really crucial. If this would be the only thing you got from this presentation, it was totally worth it. So just a quick insight. We are talking about a set of assumptions people tend to have about distributed systems, like the network is reliable, latency is 0, bandwidth is infinite, topology doesn't change, and so on. And this makes distributed transactions quite challenging. A classic approach how to tackle distributed transactions is the two-phase commit. The point of 2PC is it performs tentative operations first, and if all succeed, the commits are confirmed. So basically, it prepares the operation which is valid for a certain amount of time or until acknowledged. And this is possible to implement in a reactive way using asynchronous messages. Of course, we need to have at least one delivery guarantee, and therefore we need to have some kind of persistent storage. And also we have to take care of the duplication, or we have to use idempotent messages, and so on. But the main problems are it does not scale well, it's slow, and has certain deadlock issues. As I said in the beginning, it was possible to implement this in Akka, but there is a better way. And that's the Saga pattern. Saga is a real-world solution how to tackle distributed transactions. The point of Saga is that each of the local commits also contains a counterpart. The counterpart is a competent action of the corresponding transaction. The textbook example is that we have commits or sub-transactions, if you will, like book a hotel, buy tickets, rent a car, with competent actions like cancel the hotel or the car, and so on. And if something goes wrong, we apply all these competent action and reverse the transaction. Again, we have to take care of requirements like at least once delivery, the duplication, and so on. But this is the way you should go. But there is an alternative option. Try to avoid distributed transactions where possible, meaning that every business event needs to result in a single synchronous commit. And the other data sources could be updated asynchronously. So basically, we are going to give up all or nothing approach, and we are going to introduce eventual consistency in our system. And this is often the best thing we can do. So the outcome of this section should be distributed transactions are hard, expensive, fragile, and do not scale well. And it should be avoided where possible. If you cannot avoid them, go for the Saga pattern-based implementation. And now, long-tail latencies. So consider a system where each service typically responds in 10 millis, but with 99th percentile latency of 1 second. The distribution could look like this. The latencies we would expect are green, long tails are orange. So 99th percentile responses could be like 30 times slower, and in case of 99.9 percentile, it could be like 50 times slower. And by the way, these graphs also show us how important it is to study whole latency distributions, not just means. Using means only, this problem could be overlooked easily. The 99th percentile of 30 millis means that one request in 100 experiences 30 millis latency instead of expected, let's say, 1 millisecond. Moreover, most of our systems are distributed microservices, so one request can create a bunch of other requests in our system. For example, let's say one client request generates 10 sub-requests, and assume there's a 1% probability of hitting a slow service. So we got 9.5% chance the request is affected by the slow response. Long tails can be caused by various reasons like hardware or network issues, architecture, implementation problems, and so on. But it's important to realize it is not just a noise or some peaks caused by power users. It is a real problem. Sorry. Usually, when we are facing a problem, we try to sort it out, do we? So a general approach to tackle long tails is following. Firstly, try to narrow the problem as much as possible. Distributed systems are usually quite complex, so every bit counts. When we Yeah, then we should isolate it in a test environment and start measure and monitor everything. If, if everything goes fine, we should be able to identify and fix the problem. But it is usually not that easy. Actually, it is usually very hard. It could take weeks of investigation with an uncertain result. So if you are struggling to tackle a problem, there might be a better way. And that's tolerating long tails in a similar way how we tolerate failures. There is a bunch of approaches, so let me go through that. Edging requests, meaning sending the same request to multiple servers and use whatever comes back first. Just a very important note, to avoid doubling or tripling your load, do not send the hedging request immediately, but try to wait until the original request has been outstanding for more than like 95th percentile. So additional load should be around 5%, but the long tail should be shortened significantly. Then we have tied requests. It means instead of delaying before sending out a hedge request, we enqueue requests simultaneously on multiple servers, and we also tie them together with information about the others. When the first server processes the request, it can tell the others to cancel it from their queues. In a real Google system, this reduced median latency by 16%, and the 99.9th percentile was reduced by 40%. Selectively increase the application factors. This one is pretty obvious. Try to have more copies of things which you find more important. We can also try to temporarily exclude the slow machine from our operations. Since the source of problems might be temporary, we can continue to send shadow requests to the machine and monitor it. If the problem disappears, we can put it back. Consider good enough responses, meaning responding with incomplete results in exchange for better end-to-end latency. And the last one, hardware update can be the fastest and a reasonably cheap way to tackle the problem. So consider this as well. So that was the last topic I wanted to talk about, but before we finish, I got a couple of points I'd like to mention at least, aka haven't enough time topics. The first one is monitoring. I don't want to stress here how important monitoring is, because we all know it provides a crucial view of what's really happening inside our applications. If any one of you guys doesn't agree, let's catch up in a minute. So what options do we have here? If you have the Lightbend subscription, the simplest path is to use its inbuilt monitoring component called Cinnamon, which is super easy to use and provides quite a lot of features. And it is also tightly coupled with actor systems. If it is good or bad, I leave it up to you. From the third-party options, my personal favorite is Common, which offers very rich functionalities. And by the way, it is based on forked Akka. And now the point I want to stress about. Try to implement and start using monitoring as soon as possible, not when performance tests, 2 weeks before production went wrong. The next thing I want to mention here are network partition. A fundamental problem in distributed system is that network partitions, machine crashes, or just unresponsive services are indistinguishable for the observer. So when there is a crash, we want to remove the node from the cluster immediately. And when we have a transient problem, we want to wait for a while, as it may heal itself. Apparently, these two cases are in conflict with each other. This problem is notoriously hard, and it's causing a lot of headaches. And a really bad thing is that these things happen surprisingly common in real-world systems. The Akka cluster has a failure detector that will notice network partitions or machine crashes, but as I said, it cannot distinguish between them. It just uses periodic Hierarchies to check if other nodes are available and healthy. And also, detecting a problem is just the first step. It has to tackle it somehow. The naive approach is to remove an unreachable node from the cluster after a timeout. This works fine for, let's say, failures and short network partitions, but not for longer partitions, because both sides of the cluster will see the other side as unreachable, and after a while, it may remove it from their clusters. So if this happens, the applications is things like cluster singletons, sharding, or persistent actors, then we got a huge problem. There is a concept called split brain resolver, or SBR, if you will, which tries to tackle this. Just to be clear, this is not a silver bullet which makes network reliable. It is pretty much risk mitigation. So basically what it does, it attempts to sort out split brain by shutting down one of the partitions. I don't want to talk about implementation details here, but it provides a bunch of strategies how to tackle that, like kill the smaller partition or the younger partition, or keep the partition with a particular node, and so on. And if configured correctly, we can limit the consequences of split brain scenarios. I'm convinced that having SBR on board is a must when implementing in distributed systems. Akka provides its own SBR, but you can use it only if you have the subscription. And I'm not aware of any production-ready open source solution. So you can either write your own, which is definitely an interesting exercise, or you may go for a subscription. Booking. Risk one is quite tedious, but I wanted to mention it at least. Try to avoid where possible. If you need to block, use dedicated dispatcher/thread pool for that. Also, you can try to take advantage of Scala's blocking hint, which may improve performance and help to avoid potential deadlock in some cases. I have seen a couple of times that people try to achieve isolation within a microservice by creating multiple actor systems. And I don't think it's a good idea. Akka provides nice bulk heading features, so use them instead. Of course, it's absolutely OK when you introduce another actor system through various libraries like Kafka or Cassandra drivers, monitoring, and so on. Their creators just wanted to hide their actors from you, and that's absolutely OK. But now, the number of systems you manually create in your particular microservice should be very close to 1. And now the questions, and also feel free to share common problems you guys faced. Yeah, and the last and favorite slide, we are also hiring. Thank you.
Hello, thank you for your talk. My question is, do you know, is there any visualized monitoring utility coming to monitor cluster?
Yeah, there's definitely a bunch of tools for monitoring and visualization of that. My favorite is Datadog, if it helps.
Excuse me?
My favorite one is Datadog, which you are using quite common.
OK, thank you.
OK, so thank you very much.